All right, we will finish the park on the box today, but first we'll go through the quiz. So name one of the two boundary conditions. Extra credit if you named the other. The two boundary conditions were the wave function must be continuous. You can't have a jump in the wave function. And so that's why we set at boundary x equals 0, psi 1 equals psi 2. And at boundary x equals L, psi 2 equals psi 3. So that was the first boundary condition. And that's the one that I expected you to come up with because that's the one we used. The other boundary condition we didn't use because we had the special case. The other boundary is that the derivative of the wave function must be continuous, except when v equals infinity. And so since our boundary was v equals infinity, we were at the exception, so we didn't apply that one. So that was the one that was for extra credit, was the slope being continuous. And as I said when we talked about it, we will later on see exactly why that is and what it is if it's an infinite potential instead of a finite potential. Okay, number 2. What does orthonormal mean? 2 words. So what does that mean? Okay, so you wrote the integral from minus infinity to infinity of psi n star psi m dx equals Kronecker delta nm. Okay, that's 0 would be the ortho part. Orthogonal means that they are mutually orthogonal, which is this equation for n not equal to m. And then the normal, at this point, we'll just say normalized. At this point, I have full confidence that you know what that means without having to go into any detail. Number 3, under what condition can we separate, and this one was the trickiest one of all of them. Under what condition can we separate the time-dependent Schrodinger equation into a time portion and a spatial portion? No, it was if v is not a function of time. If v is a function of time, then we can't separate them. The process we did was we said, well, psi is a function of x and time, so we can write psi as a function of x times a function of time. And then each term we could divide to get rid of either time or position. Except for the potential energy function, you could only do it if it's not a function of time. If it's a function of time, you can't get rid of the time portion. And so the potential energy function had to not be a function of time, which is the conditions that we will use everywhere in this class.
But because of the weird math that we had to do, we had to divide by sine of x and pi of t, we also said that psi cannot equal 0.
Well, psi, look at psi again. Oh, no. Psi cannot be identically 0. That is, it can't be the trivial solution. Otherwise, our solution was, or what we did showed for everywhere where psi is not 0, then it was acceptable, the math we did. And so honestly, I'm sure there is some hand-waving argument to say, and because it works everywhere where psi is not zero, and psi is generally not zero or something like that, but I don't know exactly how to resolve it. It's not a lot. It's just, and it's cold enough that I'll be able to sweep it up instead of shovel it up. Okay, the last one. How many stationary states does a particle in the box have available to it? Yes. Has an infinite number of states from n equals 1 to any integer with any positive integer. All right, now just reviewing our solutions. We have the solutions here. The psi sub n's all have the same normalization constant, square root 2 over L, sine of n pi over Lx. The energy was h bar squared pi squared over 2ml squared n squared for each of those states. So if n equals 1, you're in the lowest energy state, and you have just one hump on your wave function. N equals 2, you're in the second energy state, and you have one up and one down, and so on. Oh, hey, look. Remember I said I didn't remember this? I didn't notice that it was right there on the slide. Remember I got out. Yeah, I got out the computer and did a search. That was genius of me. Anyway, moving on. We had Dirichlet's theorem that says that we should be able to write any function as a linear combination of our wave functions, provided that we have complete solutions, that we have all of the possible directions, if you will, all the possible unit vectors for our wave functions. So think of your wave function as a unit vector in this case. And we're saying any vector can be a magnitude in each of the different unit direction values, and you can describe that vector. That's what this is saying. To me, that makes a lot more sense to think about it that way than any other way. Does it sound reasonable to you?
The function is a unit vector?
No, think of each of your psi's, each of your wave functions, each of your eigenvectors as unit vectors.
We can call them eigenvectors now?
They are eigenvectors. Oh. That is a name for them. Eigenfunctors and eigenvectors are the same thing.
What are we doing with the homework?
I postponed it for a week because I looked at it and there's like one problem that is actually relevant to where we are. I'm sure I'll have to then cascade the rest of them down at some point, but that's where I am right now. So obviously the one that's due next week won't be due next week. This one's due next week. Thank you for reminding me. And then we have the lower function for, I was asking, does that make sense to think of these as unit vectors? Each of our solutions is a unit vector in the solution space for a particle's.
It does.
What does it look like in a particle box situation?
Well, we're going to do an example of what it looks like on the next slide. So I actually saw this is also an example that's from the textbooks, like example 2.7. So in case I screw up, you can follow along, right? It's example 2.7 on page 39. So that's what we're going to do here. We have a particle in a box. First thing we want to do is normalize it. A is the normalization constant. Oh, look, I brought the integral table, not noticing that I had also put my integral I need right there. So first we'll normalize it, and then we'll express it in terms of the stationary states, finding the coefficient C sub n. So this is what does it look like in real life? So we have created a state by carefully manipulating our system so that the probability function, the psi, the wave function, is going like this, right? The first thing is to sketch it. So this is the easiest thing in the world to sketch. So here's my box, x equals 0, x equals L. there's what it looks like. That's what my size function of x looks like. And it reaches a maximum value here of AL over 2. Now, before I even move on, what's the probability density look like? That's the wave function. What does the probability density look like?
That squared.
It's going to be that squared. So it's going to be like that. It's more peaked in the center for the probability. Now we want to normalize it. So what is our normalization? I'm going to, while I'm talking, put in some pages. What is our normalization calculation? How do we do that?
Well, yeah, an integral from 0 to L really of psi squared, or psi star, psi x dx.
Okay, now I shortcutted this. I put 0 to L instead of minus infinity to plus infinity because we know that it's not existent outside of the box. So I just have my integral 0 to L. So that's going to be integral from 0 to L over 2 of the first one, which is AX. Now I did that when I'm teaching class. I do things in obnoxiously long form. Actually, when I'm trying to explain things to students as well, I do them in obnoxiously long form because I want to make sure we understand where I got things from. So I have from 0 to L over 2 is the first half of the box. Because I have a different function the first half and the second half, that's why I have to break it into pieces. So I put AX with a star outside. That star means it's the complex conjugate, but if A is real and X is real, that star means nothing to me, right? It's not changing anything. But I put it there just so we don't forget that that's part of the process. And then I have to do the second half of the box. And this time I'm not going to write that because it's annoying. So I have to do both of these integrals and then solve to find what A is. So, of course, life is full of fun. 1 equals A mod squared. I can't help it. I put A mod squared even though I just said I'm going to choose the real value. Integral from 0 to L over 2 of x squared dx plus A mod squared. Integral from L over 2 to L of L squared minus 2LX plus x squared dx. In case you're wondering about the thing in parentheses there, that's just from multiplying L minus x times L minus x. So yeah, we did. Except for we didn't finish it. Yeah, somebody said, oh, we can cancel those out when you can't. And this time I did not put the 2 on top and the 2 on bottom. Right. We had a 2 over 2, and that was just annoying. And now I have to put in my limits. Two cubed is 8. 8 times 3, 24. Okay, so there I've color coded for each of the terms. And now I have to combine them. So I'm going to combine them carefully this time. And I have, every term has an L cubed. So I can factor out the L cubed and not have to worry about that. And I have 1 over 24 plus 1 minus 1/2 minus 1 plus 1/4 plus 1/3 minus 1 over 24. And I'm going to make sure this 3 looks different than my 2. And now I will be careful. 1/24 and minus 1/24 add to 0. Plus 1 and minus 1 add to 0. And I'm left with minus 1/2 plus 1/4 plus 1/3. So going to a common denominator, the common denominator is 12. So that's 6/12, 3/12, and 4/12. So 3 plus 4 minus 6 is 1. Now we can finish up. Now we can say, aha, A mod squared must be equal to 12 over L cubed. Therefore, A, taking the positive real result, square root of 12 over L cubed. So there, I believe I've normalized it correctly. I believe so. Does anybody? Okay, I'll go with that. It's not beautiful. Now we want to find these coefficients C sub n. So C sub n is by definition the integral of psi star sub n times my function, which in this case is going to be the capital psi. Put it in blue to indicate capital. And technically it's minus infinity plus infinity, but once again, that's going to go to from 0 to L in our case. So that's equal to, putting in our function, we have 2 pieces because we have the 2 psi's. And psi star is square root of 2 over L sine of n pi x over L. So I put in my psi star. And now my psi for the first portion is going to be square root of 12 over L cubed. That was the normalization constant we found, times, and I actually want to change the color of this. X dx. Then I have the second part. That's only the first part. The second part is going to be I ran out of space on my D. Uh-oh. Bring that a little closer and I'm good. So that's putting in the integral to find the C sub n values. And now we have to do our stinking integrals. So notice each one of these, square root of 2 times square root of 12 is square root of 24. 1 over the square root of L times 1 over the square root of L cubed is 1 over L squared. So I can bring out square root of 24 over L squared for everything. And then I have integral from 0 to L over 2 sine of n pi x over L x dx plus integral from L over 2 to L of sine n pi x over L times L minus x dx. Which logically I'm going to break into 3 integrals now, because why do 2 when you can do 3? Right? Logic that you parents would always tell you would be ridiculous. Yeah, that was a bad idea. Notice I changed the order so I'd have the 2 integrals that are identical except for the limits together. And I put the constant outside on that last integral. Ready to go to town? Let's just remind ourselves here this integral. Integral of x sine bx dx is 1 over b squared sine bx minus x over b cosine bx. So in this case, b is n pi over L. So if b is n pi over L, 1 over b squared is L squared over n squared pi squared. And then it was sine and I'm going to copy and gotta hide that first. I'm going to duplicate this just to save myself time. I know you can't do this. Duplicate. Minus, oops, didn't want that one. Minus the same integral, but with the limits changed from, right, that's the red integral. And then my last one, integral of sine n pi over L x dx is L over n pi, so that's going to make L squared over n pi when I combine with the other constant. And I believe integral of sine gives you a negative, right? Change that sine. And that has limits from L over 2 to L. This is what it looks like, Chad. Probably wish you hadn't asked now, right? So now we put in our limits. So we have a couple of different things to consider. We have L over 2 and Z. Well, let me put in the limits and then we'll consider those. So putting in the limits, Notice now each term had an L squared on top. We had an L squared here, an L squared here, and an L squared here. And so those are going to cancel with this L squared, so I can just drop that one out. The n pi's not so quick, but the L's I can get rid of. So this is equal to square root of 2L. It was 24. I dropped a slash somewhere. Yes, it was 24. Wow, that makes such a difference too. There's units involved. Thank you. Okay, so I'm going to have sine of n pi over 2 divided by n squared pi squared. That's the first term because when I put in the lower limit, sine of 0 is 0. Then for the second one, I'm going to have over n squared pi squared for the second and third terms as well. So I extended my divider so I have the same denominator. I'll have minus well, what is sine of n pi? That's always going to be 0. And notice I just have 2 of the sine n pi over 2 terms. So that's the first 2 limits there. And then for the last one, I have minus cosine of n pi, which is 1. Actually, it's plus or minus 1. Plus cosine of n pi over 2, all divided by n pi. So cosine of n pi over 2, it depends on n. If n is an odd number, it's 0. If n is an even number, it's going to be minus 1 or plus 1. The first one is going to be plus or minus 1. So I'm going to try to write this in as simple form as I can. Those rules for the sine and cosine. So we have 2 over n squared pi squared. And then we had sine of n pi over 2. Well, I can't really simplify that right now. And then I have minus cosine of n pi is going to be minus 1 raised to the n. That's one I can simplify now. Because if n is 1, then it's cosine of pi, which is minus 1. Oh. I put a divider and then I didn't change the sign because I had a minus out front. That's right. I should have had minus the cosine n pi and then plus the cosine of n pi over 2. But since I put the same divisor, this line here, I combined them together means that I had to put my sign there to make it positive.
So wait, can you explain again the minus making it?
Yes. Cosine of n pi is alternating between +1 and -1. And so -1 raised to the n will also alternate between +1 and -1. So that was a way of writing it simpler because it looks simpler than having the cosine stuff out there. And people will see it quicker. Now the sine n pi over 2, we have to worry about if n is even or odd. And we go through different iterations. So I am just going to go ahead now and take this function and calculate c sub 1, c sub 2, c sub 3, and I will stop after 3. So, oh goodness. I'm at the end of this page. I don't want to go to the next page. My experience is most of the time I don't get this copied right. Okay, I'm going to first do duplicate, then Control X. Well, that didn't seem to do anything. Okay, Control copy, and then delete. Please, please work. There it is. I didn't want to have to try to remember it. So, c sub 1 is equal to square root of 24. Sine of pi over 2 is 0. 0? No. Sine of pi over 2 is 1. So that's going to be 2 over pi squared minus, and then I have -1 raised to 1 is -1. And cosine of pi over 2 is 0. Oops. So that should be C1 if I made no errors. I can't verify that I made no errors. I don't think I did, right, but I could have. C sub 2. Now we put in n equals 2. We still have square root of 24 on top. And I'm going to have 2 over 4 pi squared times, sine of pi is 0. So let me just erase that since sine of pi is 0. I'm going to have minus 1 squared, which is +1. And cosine of pi is -1 all over 2 pi. So that's +1 minus a -1, so +1 again. So that's +2 with the minus sign out front. 2 over 2 cancels, and it's just square root of 24 over pi. Now, I am getting myself a little concerned. What is square root of 24? It's bigger than 4, right? The square root of 16 is 4. So these c's are bigger than 1, which has me concerned because the c's have to be less than 1, because the sum of all the c's has to be 1. So I did make a mistake somewhere. Well, no, square root of 24 is not 1.56. Yeah, but when you divide by pi. So I made a mistake somewhere here because that cannot be. Where did I make that mistake? Square 24 over L cubed. Square 24 over L cubed. Y'all have that. Hope not. that would be wonderful. Let's go back and look at that. I hate to make mistakes, but I hate to leave them more than I hate to make them. A was square root 12. 12 over L cubed. We had, no, I believe that's right. Yeah, I broke it. Wow. Now I have to sit down and figure out where I made my mistake. It's embarrassing, especially because it's not my first time doing it. But these cannot be correct because they have to be less than 1. Because you have to have we haven't gotten to that yet. but you have to have the sum of them adds up to 1. Yeah, the sum of them squared. That's right. So I have a mistake somewhere, and it's kind of futile to I even calculate the third one if I realize these aren't right. So I'm going to move on to the next slide, and I will come back and show you where I made my error tomorrow. You guys will be here for class tomorrow? Just making sure. I'm planning on leaving right after class is over, and if you guys aren't going to be here, that would be stuck. Excellent. Okay, we're going to start in now on the harmonic oscillator. No, that was last class. Oh, well, I did go. You're right. I did go over last class period. That makes this a good stopping point. Good call.